Hi, so this video will go over section 5.1 titled Probability Rules. So we have 5 objectives in this section that we want to look at. We want to understand random processes and the law of large numbers. 2, be able to apply the rules of probability. We want to compute and interpret probabilities using the empirical and the classical method. And then lastly, recognize and interpret subjective probabilities. Right? So the first thing that we want to do is understand random processes and the law of large numbers. So the word random suggests that suggests that we have an unpredictable outcome, right? So predicting the outcome while facing uncertainty can be challenging. Here is a well-known example, right? So can you predict the outcome of rolling a single six-sided die for one particular roll? That would be challenging. However, we are able to determine the proportion of times we observe rolling a 2 over many rolls of the die. The process of rolling a single die many times and recording the outcomes is a simulation, right? So a simulation is a technique that we're going to use to recreate a random event. The goal in simulations is to measure how often a goal is observed, right? So we could do a simulation like on a computer, or you could do it, in person, right? So, for example, if I wanted to roll a die, I could roll a die 1,000 times on my own, or I could use a computer to kind of simulate that, right? So, what we want to do is this rolling a die activity, and we're going to investigate basically what the law of large numbers is, right? So you can see the directions here for what we're going to do. So we're going to create the applet in StatCrunch, right? So I'm going to pull StatCrunch here. Oh, and then I noticed I think there's a typo in these notes. So instead of saying let the number of sides by 10, this should say B6. B6, right? Instead of by 10. That is a typo. Right, so what you'll do is go to applets and then simulation and then dice rolling, and then for number of sides you're going to let that be 6, the number of dice to roll is 1, and then you're going to hit compute, right? And then it says under events in the applet, notice for the sum of one roll, use a pull down menu and select equals. So we want to select this and do equals and 4. Hit 4 in the box. And it says click on convergence, right? So click on convergence. So now we're going to run 5 runs. We're going to click it 4 times to roll 20 times, right? So I'll click it once, twice, 3 times, oops, well, hang on, this says equals 64, that should just be 4. Sorry, I must have hit a typo or hit an extra key. So we have 15 runs, and it looks like it corrected itself in the simulation, right? So then I hit 5 runs again. Right, so we've done a total of 20 times. So notice this count, right? This means that we've, out of the 20 times we've rolled a die, we've gotten 2 4s, and the proportion would be 2 divided by 20, which is 1/10, right? 0.1, right? And this graph, right, just shows, each dot represents a roll, and that would be the, it's showing the proportion after each roll of getting rolling a 4, right? So on the notes, it just asks us to record what proportion of the rolls resulted in a 4 being rolled, right? So that proportion was 0.1. Right, so 10% of the rules for this simulation was a 4. Right, so on the next page on the notes, it says to click 5 runs 4 more times for a total of 40 rolls, right? So we want to get up to 40 rolls. Right, so there's 40 rolls, and notice the proportion now is 0.125, right? So I would click, so I just need to write that down in my notes for part B. So we got 0.125, I believe it was, right? Right, and so just to point something out too, the numbers I'm writing down are what I'm getting in my simulation, right? So the 0.1 is from our simulation, right? If you wanted to use the printout, this one just happened to also match 0.2 in this case, right? This is another time of doing it, so it won't necessarily be the same. So we got 0.125 in what we're doing right now, but if we look at the picture, it was 0.15 when the author did this, right, during this time when he made these notes. So then part C, it says to click reset and then click 1,000 runs, right, is what we want to do next. So I'm going to click reset and then click 1,000 runs, and what the proportion we get is 0.16, 0.167. Right, so it's saying, what happens to the relative frequency with which a 4 is observed as the number of rolls increase, right? So what you want to notice, right, is that notice like we have like this leveling out thing happening, right? So it's like going up and down, oscillating, and then it's starting to like go flat, right around this value, right? And if you could imagine, if you just think about this in general, right, the probability of rolling a 4 would be equal to 1 divided by 6, right? Because there's 1 4 on a die, and there are 6 sides, right? So if you take, 1 divided by 6 in your calculator, right? So if I take 1 divided by 6, this is equal to 0.16666 repeating, right? So in other words, 0.167 roughly if we round, right? So that's exactly what we were experiencing with doing this simulation 1,000 times, right? So this idea, as we're going to see, is known as the law of large numbers. Right. Let's see. Yeah, we did that. So this next part says click reset, click 1,000 runs. What proportion of rolls in a 4 being rolled? What happens to the relative frequency in 4 observed as the number of rolls increase? Right, so let's try it again. So basically just repeating that 1,000 rolls. So I'm going to hit reset and then hit 1,000 runs again, and we get 0.162. Right? So after doing this again, what we get is 0.162 for the proportion. So the result is not the same, right? So the result is not the same as part C. In the behavior in the fewer rules is not the same either, right? So if we compare, what happens in the short rules, right? So, like this first part here, it didn't match exactly either, right? So then it says based on the results of part C and D, what would you conjecture is the probability of rolling a 4 with a single 10-sided die, right? So rolling a 4 on a single-sided 10-sided die would be 1/10, right? Because there's 1 4 out of 10 options, right? So in other words, 0.1, right? So the idea is, if I were to change this, where there are 10 sides on a die, and if I looked at this when this is equal to the number 4, right, and if I did 1,000 runs, oops, I gotta hit conversions, right, so we see that, right, notice this is like flattening out, right, and the curve is flattening out right around where what we call like the theoretical probability would be, which is 0.1, right? So the proportion is 0.098, which is really close to 0.1. So if I keep doing this, like if I hit 1,000 runs again, 1,000 runs again, and I keep doing this a whole bunch of times, notice we're getting closer and closer and closer to being just equal to 0.1. Right, so we've done this 21,000 times so far, right? And I could keep hitting this all day, and we're getting closer and closer to 2.1. Right? So a random process represents scenarios where the outcome of any particular trial of an experiment is unknown, but the proportion or relative frequency, right, which we've talked about, a particular outcome is observed approaches a specific value as the number of trials increases, right? So probability is a measure of the likelihood of a random phenomena or chances behavior occurring. Probability deals with experiments that yield random short-term results or outcomes, yet reveal long-term predictability. The long-term proportion in which a certain outcome is observed is the probability of that outcome, right? So the idea is, if I flip a coin 1,000,000 times, right, how many heads and how many tails would I expect, right? So, it's agreed upon that, a coin is, symmetrical, and the physics of it is, it only has two options to land on, a head or a tail. It's possible that if you flipped a coin, it could stand straight up, but that's really, really unlikely, especially because the coin is so thin. That doesn't really happen, right? That would happen like very rare, like maybe 1 out of 10 million times of flipping a coin, right? So that one, that chance of that happening is so small that we say that rolling, flipping a head is 50% and flipping a tail is 50%, right? It's not because there are two options. The reason why it's 50%, it's more important focusing on that the coin is symmetrical, and it makes sense that not one side is more likely than the other side, right? It seems reasonable that each side would be 50%. But you could have, for example, if you had a die where it was loaded, like a weight was on one end, that's not going to be what we call equally likely probability for all of the outcomes, right? So not everything is not always going to be equally likely. So then here, the law of large numbers, right? The idea with this is that as the number of repetitions of a probability experiment increases, the proportion with which a certain outcome is observed gets closer to the probability of the outcome, right? It gets closer and closer to the true probability of the outcome, right? So I tried to show that a little bit with that applet right here, where I've hit this 26,000 times. I could keep hitting 1,000 runs more and more, and the more runs we do, the closer and closer it gets to the true probability, which is 0.1, right? Because it flattens out. Right, so this is the idea of law of large numbers, right? So in other words, when you do this a large number, like thousands of times, the proportion is going to approach the true probability, right? So that's what that was trying to illustrate. And I have this other website that we could use to try to estimate this as well. So this is simulating flipping a coin. So here, something interesting is we can set the probability of heads, right? And also the number of tosses. So I'm going to put the number of tosses all the way up, and I'm going to hit toss, and I'm going to so I'm going to keep hitting it a bunch of times. Right, and what you want to notice, is initially it kind of goes crazy up and down, but as we start to get like a large number of tosses, that's when it starts to level out and flatten out at the true probability, right? And if I check mark this box, that green line is the true probability, right? So you can see how it fluctuates. It's going all over the place, and then as I do more and more flips, we're going to be closer and closer and closer to that line. Right, so we've done 1,000 tosses so far, and the proportion of me getting heads, right, is 49.2%, right? So it's getting really, really close to 50%, right? And so to illustrate that as well, so if I hit reset, something I can do is I can change the probability of heads, let's say maybe to like 0.75, right? So in other words, I have this coin where I get a probability of heads, more often than tails, right? So maybe there's some kind of weight there where it the true probability is, if I flip a coin 4 times, I would, expect, about 3 of them to be heads and 1 to be a tail. So I can click, show the true probability. That's going to show up at 0.75, right? And then I can hit toss. And you can see again, so initially it's kind of wild, right, going up and down. And then as the more tosses I do, it's going to get closer and closer to that true probability. Right, so I want to do, let's just do at least 1,000 rolls, or not rolls in this case, tosses, right, flips. Right, so we get, so it comes out to be about 0.748, which is really close to the true probability of 0.75, right? So this is the idea of large numbers. As your number of trials goes, approaches infinity essentially, right, goes on really, really large, it's going to approach the true probability. Right. So hopefully after illustrating that, you have a better understanding of the law of large numbers. Right. So here's another example illustrating the law of large numbers. It says your daily commute to work has you going through an intersection where the light always seems to be red. You start recording data to determine the likelihood of arriving at a light while it is red. The data contains the day number and whether the light was red or not for 200 consecutive days in which you drove to work. In the data set, the column red shows a series of zeros and ones. In that column, a 0 indicates the light was not red, and a 1 indicates the light was red, right? So in other words, like a yes, no. The column aggregate red represents the cumulative number of times the light was red. And it tells us to open this file from the Sully stats group, but I had trouble locating that file, but I think we can get what we need from these screenshots in the notes, right? So, it says what proportion of the days was the light red after 15 days, right? So we have this aggregate proportion, right, for 15 days, so we can see that number is 0.466. It looks like 6 repeating, right? So like 0.467. And then so what proportion of the days was the light red after 30 days, right? So I'm looking for day 30. So that proportion was 0.567 roughly, right? And then part C says, were you stopped by the train on the 40th day, right? So if I look on the 40th day, the 1 here tells me yes, right? So 1 is yes and the 0 is no. And then now it says graph the cumulative proportion of days. The light was red against the number of days, right? So notice, initially, again, it's kind of like crazy, but as the days gets bigger, it's starting to flatten out, where the true probability is, right? So maybe somewhere along this green line is where that true probability lies, right? And obviously, the more trials we do this, the closer we're going to get to that value, right? So now it says, what is the estimate of the probability of being stuck at a red light at this intersection during your commute, right? So we would estimate the probability of being stuck at a red light was 0.625, right? Because that's what the proportion that we saw after 200 days. It seems to be approaching that value, right? And that's in line with estimate, like where I drew the line, right? It's reasonable that this is somewhere around 0.625. Right, so the next thing that we want to talk about is the law of large numbers versus the non-existent law of averages. So the law of large numbers has an intuitive feel, that is, it seems to be common sense, right? So however, the law of large numbers is often interpreted as a non-existent law called the law of averages by folks who misunderstand the law of large numbers, right? So this is often the case in baseball, and I hear this all the time. My son plays travel baseball. So it says, for example, in baseball, you may hear an announcer say that a certain player is due to get a hit because he has gone a number of at-bats without getting a hit, right? Or you may hear a mother of 4 boys say she is more likely to have a girl now. In both instances, the confusion is between what happens in the long run, which is the law of large numbers, with what might happen on the next trial of a probability experiment, right? That is to say, given that you had 4 boys, you are due for a girl with your 5th child. No, the likelihood of a girl is the same on the 5th child as it was for the 1st child. Think of it this way. The biology of determining the gender of a child does not look back at the first 4 trials, the first 4 children, and say, okay, it's time for a girl. Another way to think about this is that the trials are memoryless, right? That is to say, the trials don't recall what has happened in the past. They only consider the next trial, right? So in other words, I think the idea is, let's say someone has a batting average of like 0.3, right? And they're up to bat, and they've been in a slump. Let's say last 10 at bats they haven't gotten one hit, right? So in baseball they might say, well he's due because he bats about 0.3, so he's got to be batting sometime soon. So that's not necessarily true, right? Because you can't predict what's going to happen the next time, and also in baseball you might have 10 hits, 10 out of 10 hits in one game, or one game you might get 0 hits, right? You have off days. It's not very predictable. So the idea of the law of large numbers is, if someone gets on base 30% of the time, then the law of large numbers is talking about overdoing lots of games, right? So after 1,000 at bats, you might expect about 30%, where it's not going to predict in the short outcome, right? Like what's happening next. So that's the idea with that, is that's not true, right? To say that. So an activity that we can walk through is illustrating this, and it's assuming the likelihood of having a girl equals the likelihood of having a boy, right? So we could go through this experiment in StatCrunch ourselves, or we could, I think, probably get through this just looking at the the printout here, right? So let's see if we can give that a try. And if you want to try this on your own, feel free to follow the directions in the notes here. So it says, assume the likelihood of having a girl equals the likelihood of having a boy. So the probability of getting a boy is 0.5, right? 50%. So what we want to do is to simulate 10,000 different families where they have 4 children, where 0 represents a boy and 1 represents a girl, right? So there's the directions, and we have child 1, 2, 3, and 4, and so we would have 10,000 rows of these 1s and 0s, right? So then now what it says is determine the number of girls in each family, right? So it's saying, notice that there are 3 girls in the first family and 0 girls in the second family, and so on, right? So if we're looking at this printout, right, if I look at the first family, the first row, right, there are 3 number 1s, right? So that means there are 3 girls here. And then in the next row, that would be like the next family, there are 4 zeros listed, so that would be 0 girls, right? In other words, they're all boys, right? So in this case, there are 0 girls, right, and so on, right? So that's what that's trying for us to notice. Now what's going to happen is we can simulate having a 5th child for all 10,000 families, and we're going to name that 5th column child 5, right? So we repeat the steps up here in part A, and we add this column in here, and this column tells me the number of girls. So then it says, is the family due to have a boy? So what this table represents is a frequency table for child 5. So notice, 0 is having a girl and 1 is having a boy, and the relative frequencies are about the same still, right? They're both right around 0.5, right? So the answer, would be no, right? The family's not due to have a boy. Just because you've had 4 children, your 5th child's going to have the same likelihood of being a boy or girl, right? So in probability, an experiment is any process that can be repeated in which the results are uncertain, right? So we're talking about some terms of probability that we'll use in this chapter. So then the sample space, so that's often written like with a capital S, right, of a probability experiment, is the collection of all possible outcomes. An event is any collection of outcomes from a probability experiment. An event consists of one outcome or more than one outcome. We will denote events with one outcome, sometimes called simple events like E1, E2, E3, so forth. In general, events are denoted using capital letters such as E, right? So we might use like E, F, and so forth to represent the events. So to practice with these terms, it says, suppose we can conduct the experiment of having 2 children, identify the outcome of the probability experiment, right? So what I want to do is show you how to think about this, but using a tree diagram, right? Something that's called a tree diagram. So we have like an initial point, excuse me, which is the start of the tree diagram, and then we need to have our first child, right, which is either going to be a boy or a girl, right? And then from there, if you had a boy first, you could still have a boy or a girl. If you had a girl first, you could have a boy or a girl, right? So this is like your first child, and over here would be your second child. And then what we could do is, kind of like name the outcomes. So if I, had a boy and then a boy, right, that's one possible outcome. In other words, I have 2 boys, right? I could also follow this where it goes a boy first and then a girl. So this would be, like boy, girl. right? And so I'm gonna, instead of writing out like 2 boys, let's denote it using letters, right? So we'll use 2 letters like BB, where B is going to, of course, equal boy, G equals girl, and then the first letter written is going to be the first child, and the second letter written is going to be the second child, right? So that's one way we can easily do this. So then if I follow this path, right, this would be GB, girl, then a boy, and then here this would be 2 G's, right? A girl, girl. So these are the possible outcomes, right, in this experiment. So we want to identify the outcomes of the probability experiment, right? So you could have both boys. The first child being a boy, the second being a girl. We could have the first be a girl and the second be a boy, or both girls. Right, so that's maybe showing that in words, so you could list it out like that, or show the tree diagram. So the sample space, right, we show that with capital S and show that as a set. That would be equal to these different outcomes that we had written, like 2 B's, 2 G's, a BG, and a GB. Right, girl, boy. So then now it says define the event E as having 1 boy, right? So E would equal any of the items in the sample space, right, that meet the condition of just having 1 boy, right? So BB would not work, right, because that's 2 boys. GG would not work. Whoops, and there should not be a comma here, right? Those are together. But BG and GB, right, both of those cases, so having a boy and then a girl, or a girl and then a boy, both of those cases define having 1 boy. Right, both of those meet that. Right? So then the second learning objective is applying rules of probability, right? So the rules of probability are the following. So the probability of any event E, so we show that notation-wise as capital P of E, right? So that's a probability of E, must be greater than or equal to 0 and less than or equal to 1, right? So in other words, the probability of any event E is going to be in between 0 and 1. So it could be equal to 0 and it could be equal to 1, right? So we say that the probability of E is in between 0 and 1 inclusive, right? Meaning it includes 0 and 1. And then another thing is that the sum of the probabilities of all the outcomes must equal 1, right? Or in other words, 100%. So if I take the probability of each individual outcome in the sample space, then that equals 1. And that's what this is showing, right? So in other words, we have n outcomes possible, right? So like E1, E2, E3, E4, all the way up until we get to the last one. And then so if I take the probability of each of these events and add them up, then we get 1. Right, so maybe another way to write that is, sigma of the probability of EI is going to be equal to 1. Right, so if we add up all the probabilities of the various events, that's going to equal 1. So a probability model is going to list the possible outcomes of a probability experiment in each outcome's probability. A probability model must satisfy rules 1 and 2 of the rules of probability. Right. So here's an example of a probability model. So in a bag of peanut M&Ms, milk chocolate candies, the colors of candies can be brown, yellow, red, blue, orange, or green. Suppose that a candy is randomly selected from a bag. The table shows each color and the probability of drawing that color. Verify that this is a probability model, right? So this is a probability model. So we have to verify both of those conditions are met, right? So each of these need to be in between 0 and 1, right? Which is the case, right? All of these numbers, all of these probabilities are in between 0 and 1, right? Then the next condition is if I add all these up, we need that to be equal to 1, right? Which you can double check with your calculator, and that's true, right? So in other words, the sum of the probabilities of each of the events, so we can say, probability of E sub I is going to be equal to 1, right? If I add all these up, so if I take 0.12 plus 0.15 plus 0.12 plus 2.3 plus 2.3 plus 1.5, do that in your calculator, and you get 1. Right? So therefore, this satisfies both conditions, right? We've checked off both conditions. So some key concepts of probabilities. So if an event is impossible, the probability of the event is 0, right? So when you say something has a probability of 0, it's impossible to happen. It's definitely not happening, right? In the event that something is, if an event is a certainty, right? In other words, it's definitely happening, like no question, the probability of the event is 1, right? So the closer a probability is to 1, the more likely event will occur, right? So if like probability was like 0.9, that's really likely, right? The closer a probability is to 0, like 0.05 or something, right? That's less likely. And then an event with a probability 0.65 is expected to occur about 65 out of 100 times, right? So that's what I was meaning, like when we were doing the coin tosses, if the number of heads, if that probability was 0.75, right, that would mean that we would expect, to get 3 heads out of about 4 flips, right? 3 out of 4, right? So then an unusual event is an event that has a low probability of occurring, right? We say that's unusual. So we usually use 0.05 as the cutoff for deciding whether an event is unusual or not, right? And that number, isn't, fixed in every case, but that's often the number that we'll use, and this 0.05 is going to come up a lot. That's our typical, what we call, a typical number that we'll use at the end of the class called hypothesis testing, right? But it was also related to finding unusual numbers, because if you remember back from the empirical rule, right, if here's my z-axis and here's my normal model, right, in the middle is my z-score of 0, here's a z-score of 1, -1, 2, and -2, right? And if I look at the percentage of data that we would expect in between -2 and 2, if you remember, that's 95%, right? Because in between 1 standard deviation, that's 68%, and then within 2 standard deviations, 95%. So if you remember, in a previous section, we looked at, things that occur over here would be considered unusual, right? So it kind of goes along with that 5%, right? Because there's 100% in the curve, so that means that the total between these two tails would be 5%, right? So that's all kind of tied together, right? So then part 3, we want to be able to compute and interpret probabilities using the empirical method, right? So the empirical method is, can be often referred to as, it's an experimental probability, right? So it's a probability, or in other words, a relative frequency of doing some experiment, right? So you can see here, the probability of E is going to be, approximately equal to the relative frequency of E, which is where we take the frequency of E occurring divided by the total number of trials of experiment, right? So that's what we were doing in all the simulations, with the rolling of the die and also flipping, tossing of the coin, right? Both of those, we were calculating relative frequencies, right? So it's using the empirical method. So In this next example, we want to build a probability model from a random process, right? So Pass the Pigs is a Milton Bradley game in which pigs are used as dice. Points are earned based on the ways the pig lands. So there are 6 possible outcomes when one pig is tossed, right? And those are in the table below. A class of 52 students rolled pigs 3,939 times. The number of times each outcome occurred is recorded in the table, right? So we're given the frequencies and the item for each outcome, right? So part A, it says to use the results of the experiment to build a probability model for the way the pig lands, right? So what we need to do is figure out the total frequency, right? So if I add all these up, you should get 3,939, right? When you add up all of those numbers. So then I'm going to make another column here. And I'm just going to title this the probability. So then, to figure out the probability for the outcome side with no dot, you would take the frequency 1,344 and divide it by the total number, which was 3,939, right? So if you take 1,344, in other words, let me write it over here, right? So we're just going to take this number divided by 3,939, right? The total. So you're going to do this for all of these. Right? And then you can fill in the probability. So let me grab a calculator here. We can go split screen. Right. So if I take 1,344 divided by 3,939, right, I can get that relative frequency for that event happening. And I'm going to round to just 2 decimal spots, right? So I would do 0.34, right? And notice I'm rounding here, right? So then next, I would take 1294 divided by 3939. So I get roughly 0.33. Right, so I would do this for all of these, right? So the next one we get roughly 0.19, and then 0.09, and then so this is something I wanted to point out. So if I do the next one, like 137 divided by 3939, I get roughly 0.03 if I round to 2 decimal spots, right? But notice, it's somewhat close to 0.4. It's like almost halfway, right? But then when I take 32 divided by 3939, I get like 0.01, right? But the problem is when you add all these up, right, the total, this total should be equal to 1. If you remember from one of the conditions, right, the rules for probabilities, we want the total to be 1. But if you add these up as the way they are, it's 0.99, right? So one of these we need to bump up to 1, or add like 1%, like 0.01 back into it, right? So if I take, if I add 0.1 here, that's going to like dramatically change that probability, right? Because it's not it's not even equal to 0.01, so I would hate to bump that up to 0.02, right? So what I did was I picked to do this one and bump that up to 0.04, right? Because if you remember, 0.03 was, it was closer to 0.04 than, trying to bump up the 0.01. So you just got to kind of make a choice to see which one you would want to bump up to, add 1% back into it. Right, and if you look at these closer, you might want to do a different one. That's fine, right? But the important thing is that in order for us to have a probability model, is we need the sum of the probabilities for all the outcomes to be equal to 1, right? We need each of these to be in between 0 and 1, which they are, right? So that is a probability model for this game. So that's part A. And so part B says estimate the probability that a thrown pig lands on a side with a dot, right? So we would use our table. So the probability of getting a side with a dot outcome is approximately equal to 0.33, right? That's our estimate. And then so it says, would it be unusual to throw a leaning jowler, right? A leaning jowler, probability of getting a leaning jowler is about 0.01, right? Which is less than 0.05. So yes, it's unusual, right? So in general, we often use, remember, probabilities less than 5%, 0.05, to be considered unusual. All right, so now ready for the next page. So this is a new learning objective. So we want to compute and interpret probabilities using the classical method. So the classical method of computing probabilities requires equally likely outcomes, right? And remember, not everything's going to be equally likely, right? So like if I had a loaded dice, right? So an experiment is said to have equally likely outcomes when each outcome has the same probability of occurring, right? So in other words, if I were to roll a die, 10,000 times, I would expect us to have 1/6 of the rolls be a 1, 1/6 be a 2, 1/6 be a 3, 1/6 be a 4, 1/6 be a 5, and 1/6 be a 6, right? So we want to have like an even number of relative frequencies for each of the outcomes, right? Then we would say that's equally likely. So here's a table for computing probability using the classical method. So if an experiment has n equally likely outcomes, and if the number of ways that an event E can occur is m, then the probability of E, which is written as P of E, is the following. So the probability of E equals the number of ways that E can occur divided by the number of possible outcomes, or we said m over n, right? So if S is the sample space of the experiment, we could say the probability of E happening is, capital N of E divided by capital N of S, where capital N of E is the number of outcomes, right? So this N, you're thinking about the number of things in E, the number of things in S, right? So N of E is the number of outcomes in E, and N of S is the number of outcomes in the sample space, right? So there's some different ways to denote that. So here, an example, we're computing probabilities using the classical method. So suppose that we have a fun-sized bag of M&Ms that contains 9 brown candies, 6 yellow candies, 7 red candies, 4 orange candies, 2 blue candies, and 2 green candies. Suppose that a candy is randomly selected. So part A is, what's the probability that it is a yellow, right? So the probability of rolling a yellow, or not rolling a yellow, but picking a yellow candy, right, would be equal to the number of ways you can get a yellow divided by the total number of options, right, in S, right? So this would be equal to, so there's 6 yellow candies, so that would be 6, right? So then to figure out the total number of possible outcomes, we would need to add up all these numbers, right? So take 9 plus 6 plus 7 plus 4 plus 2 plus 2, and that should give you 30. Right, so in other words, there's 30 candies in this fun-sized bag of M&Ms. So 6 over 30, right, that's equal to 1/5, which is equal to 0.2 as a decimal, right? So the probability of getting a yellow from this using the classical method would be 20%, 0.2. So part B says, what's the probability of getting a blue, right? So the probability of randomly picking a blue candy would be equal to the number of ways you can get a blue candy divided by the total number of possible outcomes, right, in of S. So there are 2 blue candies, and we have 30 candies total, right? So it'd be 2 out of 30. So that can be reduced down to 1/15, which is equal to 0.066 repeating, right? So we have roughly, like 7% probability for picking a blue. So it says here, comment on the likelihood of the candy being yellow versus blue, right? So what we could say is that a yellow M&M is 3 times more likely to be chosen than a blue M&M, right? So in other words, to demonstrate that, if I take 1/15 times 3, that equals 1/5, right? So the 1/15 was the probability of a blue, where 1/5 was the probability of a yellow, right? So the probability of a yellow is 3 times more likely, right? So it's a lot more likely, right? So if I were to bet, so if all these candies were in a dish and you had to bet, like, trying to guess, like maybe you say a guess before you grab an M&M out of here, right? If you were betting, man, and you had to pick either blue or yellow, right? You'd want to pick yellow, right? And if you could pick any color you wanted, you'd want to pick the one that has the most frequency, which would be the brown candies, right? All right. So then now we're ready to look at the last learning objective, which is to recognize and interpret subjective probabilities, right? So the definition of a subjective probability is that it's of an outcome is a probability obtained on the basis of personal judgment, right? So you're basing the probability on personal judgment, not on any kind of experiment or any kind of theoretical probability rules to try to figure out what the probability would be, right? So for example, if an economist predicted that there's a 20% chance of recession next year, would be a subjective probability, right? It's something, it's based on personal judgment. Or like here, here's another example. So it says, in his fall 1998 article in Chance magazine, a statistician reads the sports pages, which was page 17 through 20, how Stern investigated the probabilities that a particular horse will win a race. He reports that these probabilities are based on the amount of money bet on each horse. When a probability is given that a particular horse will win a race, is this empirical, classical, or subjective probability, right? So this is subjective because it's based upon people's feelings about which horse will win the race. The probability is not based on a probability experiment or counting equally likely outcomes, right? So if those two things aren't happening, and it's based on, a personal judgment, we call that subjective probability. Hi, so one additional thing that I wanted to mention before we finish this section is looking at this outcome chart in StatCrunch, right? So this is the StatCrunch that we were working on, and this is when I was simulating ruling a 10-sided die, and we were looking at how many rules I got the event of a 4, right? So we found roughly after doing this 38,000 times, we had roughly 0.1 being the proportion, right? Which is what we would expect theoretically, right? There's 1 4, there's one way to get a 4 divided by 10 possible outcomes in the sample space. Right, and so we saw with the law of large numbers, where this is flattening out this graph right around 0.1. Right, so if I click on outcomes now, right, what this is a frequency histogram for each role. Right, so you can see that each bar, right, is about the same. In other words, we have a uniform distribution. Right, so that would mean that this die is fair. Right, that's something that we would expect. We would expect all of these rules to be or all of these bars to be about the same height, to have a uniform distribution like this, and we would expect each of these bars in this case to represent 1/10, right? So of the rules. So if I take 1/10 times 38,000, that gives me 3,800, right? So each of these frequencies are going to be right around 3,800, right? So that's 3,813, 3,740, right? So they're not going to be exact, but you'll notice that all of these are right around 3,800, right? So if this was relative frequency over here, these would line up to be about 1/10, right? All right. So hopefully that's helpful. Make sure you let me know if you have any questions. Thanks.